I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists.
Hello, everybody. My name is Tucker Hyatt, and you are at Wonderfest. Welcome to Innovation in the Search for ET with UC Berkeley's Dan Werthimer. I'm the founding director of Wonderfest. All right, our speaker tonight is Dan Werthimer. He is Chief Technologist at the Berkeley SETI Research Center, where he directs projects with names that are very cool acronyms like Serendip and Casper. For 20 years, Dan was chief scientist of SETI at Home, almost an acronym, which beautifully democratized SETI for over 5 million folks, but is in hibernation right now. Early in his astronomy career, Dan was associate professor, in the engineering and physics departments at San Francisco State University. And he taught at many foreign universities in Peru, Egypt, Ghana, Ethiopia. Dan was always one step ahead of the law during this time of his life. Long ago, Dan was a member of the Homebrew Computer Club with the likes of Steve Jobs and Steve Wozniak. According to Dan, everyone in the Homebrew Computer Club became filthy rich, except Dan. Earlier, I mentioned that Wonderfest is 25 years old. I hope I mentioned that. It was a quarter century ago that Dan Werthimer joined with Jill Tarter of the SETI Institute in presenting the first Wonderfest in-person event. That was in August of 1997. So we're almost coming up on 25 years. So it's great that we are able to welcome Dan. And I ask you to do that. Please join me now in welcoming SETI pioneer and Wonderfest old-timer, Dan Werthimer.
Thank you, Tucker. Thanks for that great introduction. Tucker mentioned that I was in this Homebrew Computer Club and I didn't become filthy rich like everybody else, but the reason is because I wanted to use those very first little microcomputers to do SETI and not to build home machines, home computers. So I didn't become rich, but I'm having a lot of fun, and I'll tell you a little bit about that. So today I want to address this question: is anybody out there? Are we alone? And I'll try to emphasize this innovation in the search for ET and some of the new searches that are going on and some of the future searches that might happen. Before I get started, I want to let you know that Tucker is one of the pioneers in SETI. He worked with us for several years at UC Berkeley. And one of the great things that Tucker developed was something we call the Gaussian search algorithm. And the idea is that when a radio telescope goes across a source, you expect the signal to get stronger and weaker. If there's another civilization transmitting on that target, it would get stronger as the telescope approaches it, and then weaker as it goes down. It should trace out this Gaussian. Can you see my cursor on the screen there?
Right. And Dan, that's because we assume that the telescope is on the Earth and the Earth's turning. So
yeah, it could be that the telescope is actually moving with the motors, or it could be that the telescope is stationary and the Earth turns. Either way, the source is going to appear to move across the telescope. And it should trace out this Gaussian pattern. And Tucker was the guy that figured out how to check to see if it's tracing out the Gaussian pattern. And it'll tell you how well the Gaussian fit, how strong it was, and how close it was to the.
Try it again.
I'm sorry, I need to do some muting here.
Okay.
Yeah.
Okay, so by the way, if anybody in the audience is talking, could you please mute your microphone? I think that's what Tucker's trying to do. Thank you. Okay, so this is kind of a theoretical approach. It's called the Drake equation. You can use this equation to calculate the number of civilizations there are in the Milky Way galaxy. The problem with this equation is to calculate this number n, all you have to do is multiply all these numbers. But the problem is we don't know what any of these numbers are. So it's a way of kind of breaking up a big problem, are we alone, into smaller problems. And I'll talk about some of these smaller problems, but it's really kind of a way to organize our thoughts about are we alone or not? It's not really meant to be a real calculation that you could just plug in the values of this equation. Frank Drake meant it as a way to organize a conference and let's talk about this subject, that subject, that subject. Not really, you can't really learn the number of civilizations with theory. You've got to go out and look. But the number of civilizations, what Frank Drake said is that you take the number of stars in the galaxy, there's about a couple 100 billion stars, and then you ask how many of those stars have planets, or what's the typical number of planets going around each star. And then you ask, this next thing is about the right environment of a planet. You're asking how many of those planets, what fraction of those planets have the right environment, the right conditions for life, the right temperature, the right chemicals where life might get started. So you start with stars, then you go to planets, and then you say how many of those have the right environment, the right conditions for life. The next little thing is, if you got a good planet, this L is about what fraction does life get started on. So you have a good planet, you've got all the right chemicals and ingredients, how often do you get life? The next factor is, if you got life, this I is for intelligence. You got life, does it evolve and become intelligence? The next factor is about communication technology. Okay, they're intelligent, but what fraction of those intelligent civilizations develop communication technologies or a way that we could detect them? And the last factor, once you meet all those criteria, the last factor is, how long do the civilization live? As soon as they develop communication technologies, do they also develop nuclear biological weapons and blow themselves up, or do they learn to live together in peace? Our star's a few billion years old. It's going to last another few billion years. So if we can get through a kind of tricky period where we're killing each other and figure out how to live in peace, we could last another few billion years. Some stars are quite a bit older than us. Our star is kind of middle-aged. It's about 5 billion years old. But some stars are 10 billion years old. So you can imagine very advanced civilizations out there. So anyway, this is kind of a whittling down process. You kind of, you start with the number of stars and planets, and then you whittle down how many of them are good places for life and how many of them have actual intelligent life and how long do they live. I want to talk a little bit about some of these factors. When Frank wrote this equation, we only knew about this very first thing, how many stars there are in the galaxy. We did not know that there were planets going around other stars. We hadn't detected any planets going around other stars. But about 25 years ago, the first planets were discovered, the first exoplanets going around other stars. And I want to tell you a little bit about that. So the first planets were discovered using something called the wiggle method. The wiggle method is that you can't see the planets directly. They're little dinky things. A million Earths would fit inside the sun. The planets don't give off light. They're right next to these really bright star things. It's like looking for a firefly next to a bright searchlight. You can't see the planet, but when the planet goes around the star, that's this white thing here, you see the planet going around the star, it pulls on the star a little bit with the gravity, and the star wiggles a little bit. It doesn't wiggle very much. It kind of moves at walking speed, a few kilometers per second. And a few meters per second. And what happens if the star is wiggling? When it's moving toward you, the colors get a little bluer. That's called blue shift. And when it's moving away from you, the colors get a little redder. So if you use your telescope and a spectrometer to look at the colors coming from the star, and you see it getting a little bluer and then a little redder and then a little bluer and then a little redder, you can deduce the presence of a planet from the star's wiggle. That's how the very first planets were discovered. A lot of that work was done here at Berkeley. And this is an example of the data coming from this experiment. Here you see the star, how fast it's moving as a function of time. And you can see it's kind of going up and down rapidly. And then it's got this slower motion as well over several years. So this is because it's got this complicated wiggling pattern, the slow thing, and then this fast thing. What's going on here is there are two planets that are perturbing the star. The fast one is a planet nearby the star, and it's going around roughly every year or two. And then this slow thing is taking about a decade to go around the planet. It's out further away from the star. Sorry, going around the star. Okay, now a more recent technique is called the occultation method. I don't know if you can see this if you have good eyes. Here's a planet getting in front of the star, and this little planet is going to block some of the light from the star. And so as the planet goes around the star, when it gets in front, the light should get a little dimmer. You can't actually see the planet, but you can see the light getting a little dimmer. And NASA built a satellite called Kepler. It's basically a big camera in space, a big telescope and camera. And it took a picture of 150,000 stars about every minute or so. And occasionally these stars would dim down a little bit. And the dimming was periodic, and that they could deduce the size by how much it dimmed, the size of the planet, and they could deduce the period by how often the star dimmed. And that's called the occultation. Occultation is when something gets in front of something else. And now we know about thousands of planets. And if you extrapolate on the little patches that Kepler and Tess have looked at, we can calculate there are about 1 trillion planets in the Milky Way galaxy. That's about 5 times more planets than there are stars. So most stars have on average 5 planets. And you can see a lot of them are, multiple planet systems. Some of them are like our own solar system. So the next question in the Drake equation, okay, you got a lot of planets. How many of them are good ones? Well, you don't want to live too close to the star. It's too hot. You don't want to live too far away. That's too cold. This thing, the green area here is called the habitable zone or the Goldilocks zone. That's where you might have a liquid water at the right distance from a star. And these missions have found several of these planets, maybe 5% of them would be in the habitable zone. So 5% of 1 trillion is a lot of planets in our galaxy that could habit life, that are the right temperature. Also, they found liquid water, and we think a lot of these planets have water and perhaps the right chemicals to get life started. So the next factor you might remember the Drake equation, okay, you got a nice planet, the Goldilocks planet, it's got liquid water. How often do you get life? That is a tricky question. We really don't know exactly how life got started on Earth. This is an example of something called the primordial soup. We think life might have gotten started in the ocean, in the deep sea thermal vents. There's a lot of energy, a lot of rich chemicals and molecules where you can make self-replicating molecules. And people have done experiments to simulate the early conditions on Earth. So we knew when Earth was forming that there was methane and ammonia and water and hydrogen. So people took these molecules and put them in a flask. And then we also knew there was lightning. So they made some sparks to kind of simulate lightning. So they didn't get life in this flask, but they did get the basic building blocks of life, the amino acids. And so they're beginning to see how you can go from very simple molecules to fairly complex molecules. And maybe eventually the amino acids could make self-replicating molecules like RNA. What about intelligence? Well, this is another unknown thing. So we know a lot about planets and how many of the planets might be in the habitable zone. But once you get into life, and then once you get into intelligence, this becomes a big unknown. And some people think that once you get simple life, it's going to become intelligent. And they point to these examples of several different things that have become intelligent on different evolutionary tracks. We're not the only intelligent creatures on the planet. Probably if we wipe ourselves out somehow, it won't take long, just maybe a million or a few million years before one of these creatures evolves to something as intelligent as we are. There are different selection pressures in evolution. It's good to be fast. It's good to have maybe a hard shell. It's good to have, but in some ecological environments, it can be advantageous to be intelligent. And so planets that have these environments where it's useful to be intelligent, there will be some selection pressure and intelligence will evolve. Okay, there may be simple life in our own backyard. A lot of people are excited about a moon going around Jupiter called Europa. And the reason there's excitement about Europa is because it's got liquid water. It's got a big ocean. The whole thing is covered with an ocean. Unfortunately, it's covered with ice. So this is solid ice. But here it's kind of warm ocean heated by the tidal forces of, as the moon goes around Jupiter. And there may be something swimming around in this liquid ocean. And we're trying to figure out, especially NASA and ESA are trying to figure out how to get through the ice and see if there's something swimming around down there. There's another moon that's quite exciting going around Saturn called Enceladus. And this has got the same thing. It's got a liquid ocean surrounded by ice. But the nice thing about Enceladus is that there are cracks in the ice, these fissures, and there are plumes. Some of the liquid ocean is squirting out in these plumes. And people are thinking about how to fly through these plumes and sample the vapor that's coming out of this ocean and see if there are some ingredients or perhaps even life itself in these plumes. Okay, I want to talk a little bit about SETI, the search for extraterrestrial intelligence. This is not about searching for primitive life, but searching for intelligent life. In particular, SETI is really a search for what we call technosignatures. It's a search for technology. It's not really a search for intelligence. We're searching for artifacts of that intelligence, the technology that might create some kind of signal or something that we could observe. Well, some of the early ideas in SETI, this is about 200 years ago, Gauss, the mathematician, suggested that we make a big geometric structure on Earth, a right triangle made out of pine trees, maybe 3, 4, 5 miles on a side, and big squares of dirt and wheat and water. And ET would look down and see that Earthlings knew about the Pythagorean theorem. It was a cool idea. Unfortunately, it was not funded. Von Littron, also a couple hundred years ago, suggested that we get in touch with ET by making a bright ring of light. So he said we should dig a ditch 20 miles across and a circular ditch, fill the ditch with kerosene, use this match not to scale, make a bright ring of fire, and ET would see that bright circle of light. Also a cool idea, not funded. Charles Crow, a couple hundred years ago, suggested that we signal the Martians by reflecting sunlight with large mirrors, reflecting the sunlight to the Martians, actually several mirrors, one where he lived in Paris and the others to outline the shape of the Big Dipper here. And the ET, the Martians, would see these bright lights on Earth and perhaps they would get in touch with us. And I think you can guess what happened with that. The first funded project was a plaque on the Pioneer 10 spacecraft. And this plaque had a little picture of the solar system with the sun and Mercury and Venus, and here's Earth, and here's the spacecraft leaving the Earth. And here's a picture of humanity and to scale with the spacecraft so they know how tall we are. These two people were originally holding hands, and NASA thought that's not a good idea because I think of one creature instead of two. These are directions to nearby pulsars. And if you have good eye, you can see there's little kind of Morse code lines here that indicate the periods of these pulsars. So they'll know which pulsars we're talking about, and they could find our sun's precise location if they also know about these pulsars in their periods. So this was kind of the first funded project was sending pornography into space. So one problem with SETI is that the kind of ideas that we think of are anthropocentric ideas. You know, we do this, maybe they'll do that. We're sending radio waves, maybe they'll send radio waves. We have television, maybe they have television. And if you kind of look back on the last 200 years of what people have been thinking, we kind of laugh at what they were doing 200 years ago, what was suggested. I think what that means is that 200 years from now, people will be laughing at the kind of stuff that we're doing at Berkeley. But I think you got to do what you know how to do, and maybe we'll get lucky. One of the ideas of how to detect primitive life would be to take a spectrum of the atmosphere of an exoplanet. And if you had a really good telescope in space, perhaps the Webb telescope will be able to do this. You could do something like this, and the spectrum might be able to tell you what molecules are in the atmosphere of the exoplanet. And for instance, it could tell you if there's water there, or maybe even chlorophyll that would tell you if there are plant life on that planet. These are very difficult measurements to make, and people are just starting to talk about how you could do this with large space-based telescopes. I don't think it'll be done in the next few years, especially this chlorophore thing. But there may be some of these simple molecules will be found, and already people are starting to do that with the large ground-based telescopes. Another way that you could search for technosignatures from a very advanced civilization would be to look at the waste heat. If they use a lot of energy, maybe they harness all the energy from their star. Maybe they surround their star with some solid structure. That's called a Dyson sphere, named after Freeman Dyson. He said that advanced civilization might be able to build these very large structures, much like, and cover them with photovoltaic cells or some way to harness that energy. And that energy would be radiated as waste heat in the infrared. And people have looked for these Dyson spheres by looking for stars that have a excess of infrared light that would indicate a lot of waste heat coming from a super civilization. It's kind of a difficult problem because when Freeman Dyson suggested this, he didn't realize this, but some stars have a lot of dust going around them, and that behaves exactly like if you built a shell going around your star. It absorbs the energy from the star, which is mostly at visible light, and then re-radiates it in the infrared as heat energy. And so it's kind of confusing. Have you found a bunch of dust going around the star, or have you found another civilization? Okay, so a lot of SETI researchers look for radio signals coming from other stars, other planets. And the motivation is, if you look at Earth, this is a plot of television power leaving the Earth as a function of time, 1940, 1950. And you can see we're getting brighter and brighter as more and more transmitters, more and more powerful transmitters. This is a log scale, so we're growing exponentially, although we're not growing as fast as we used to. We're going to more directed communication with fiber and cable and lasers and things like that, becoming more efficient rather than just broadcasting in all directions. But the early television shows I Love Lucy have gone past 10,000 stars traveling at the speed of light. The nearby stars have seen The Simpsons. So we're broadcasting all this stuff out into space. Maybe ET does that too. We even sent messages intentionally. This message was sent in 1972 from the Arecibo telescope, which has a big transmitter. This was sent for 2 minutes out to a globular cluster called M13. It'll take 25,000 years for this message to get there. The nearby stars are only a few light years away. So if you send a message to a nearby star, it might take just a few years to get there, but this was deliberately sent something far away. So if they receive it in 25,000 years and send a message back, we'll get it with a reply in 50,000 years. Anyway, this message, think pictures might be a good way to communicate. It's got the solar system with the sun and Mercury, Venus, Earth is tipped toward the person. It's got a picture of the telescope that sent it, the diameter of the telescope, the population of the humans. There's the human, there's DNA molecule. Here are some of the molecules that go into life. It was meant kind of an example of how we might communicate with ET, and the Earthlings are getting in the game where we should start thinking about the consequences of contact. Okay, so in SETI, you can think of a couple signals that you might discover. One would be an artifact of their technology that wasn't really meant, it wasn't transmitted directly toward us for communication. It's much like they would have something like radio or radar or television. It wasn't meant for us, but we could intercept it. We would know we're not alone. We probably couldn't decode the message. It wouldn't be in English. And we probably couldn't even decode the pictures. But the other possibility is that they maybe they know about us, maybe they've seen our television or radar, maybe they've seen oxygen in our atmosphere. Then they might send a deliberate signal toward Earth. And if they send us a deliberate signal, it'll probably be easy to decode with language lessons and lots of pictures. Maybe they've done it before, they've contacted primitive civilizations like ours, so they know what kind of communication works and what kind of communication doesn't work. So I'm not the first person to think of this kind of stuff. Tesla and Marconi, more than 100 years ago, both looked for radio signals. These guys were the early radio pioneers. They both looked for radio signals from ET. They actually both thought that they had found it. Turned out they were listening to distant lightning bolts, that they didn't realize that lightning creates radio waves and it can bounce around in the ionosphere and get into their radios. In the 20s, a little less than 100 years ago, the Navy did a big search for radio signals from the Martians when Mars was very close to the Earth. They asked everybody to stop transmitting, so it'd be quiet that day. They didn't find anything. The more modern search that Frank Drake did in 1960, about 60 years ago, searched, I think, 3 different stars and looked at a small range of the electromagnetic spectrum, around 1420 megahertz, one channel at a time. Today's SETI systems are much more powerful. We've got 100 billion channels at once, but this was what we call the first modern search. So at Berkeley, we have something called the Berkeley SETI Research Center. There are a couple dozen people that work on SETI, and we're funded by the Breakthrough Foundation, National Science Foundation, NASA, individual donors, and some companies that donate equipment that we use. My main motivation for doing SETI is if you find ET, you might get the Nobel Prize, and you get some cash with that, but the main thing you get is a parking permit that allows you to park right in front of the astronomy building, which would be very cool. Okay, so one of the big problems in SETI is we don't know what wavelength or what frequency. We don't even know if they're broadcasting or sending anything, but if they are, we don't know what frequency they might use. There are a lot of different frequencies across the electromagnetic spectrum. They could be broadcasting in the radio part of the spectrum, in the optical, the infrared. If you're going to do this on the ground, there are certain wavelengths or frequencies that get through the Earth's atmosphere. So that's a good place to look because it's easy to look. You don't have to go in space. And these windows are shown here. And we're starting to explore some of these windows. Right now, we can't do a thorough search of all the different wavelengths and frequencies in the whole electromagnetic spectrum. Earthlings are mostly getting in the game. We can look a little bit here, look a little bit there. We are not able yet to do a thorough search across the whole spectrum. One of the big projects at Berkeley is called Breakthrough Listen. And it uses several different telescopes around the world. I've shown here 3 of the big ones. There are 2 big radio telescopes, one in the northern hemisphere in West Virginia and one in the southern hemisphere in Australia, which can see the southern part of the sky. This one can see the northern part of the sky. They're covering a large chunk of the radio spectrum, mostly doing targeted work looking at nearby stars. This is at Lick Observatory. This is an optical telescope looking for laser lines or some sort of narrow line that is very different from kind of natural emission that you get from stars and other astronomical objects. They use this telescope was built for finding planets, for searching for planets using that first method that I talked about, the wiggle method. It's got a very good spectrometer. It was built for finding planets, but it turns out that's exactly the thing you need for looking for laser signals from other civilizations. Okay, so this is a project that Tucker was involved with. It was one of our early projects. We're still running it, although it was called Serendip. Now we're then we went on to Serendip 2, 3, 4, 5. Now we're at Serendip 6. Serendip, Jill Tarter used to work in our group, one of the early SETI pioneers. She invented this acronym, the Search for Extraterrestrial Radio Emissions from Nearby Developed Intelligent Populations. NASA requires the use of acronyms, so we have a lot of acronyms in our research. This logo was designed by our host, Tucker Hyatt. This was the first telescope that we used at the Hat Creek Observatory in Northern California, the UC Berkeley Observatory. This is an 85-foot dish. And while we were using this dish, this is what happened to it. This is the dish. Here's the pedestal. The dish used to be up here. So that put an end to our SETI research on that dish. Then we moved to this telescope, which is even bigger. This is 300 feet across in West Virginia. And while we're using this telescope, this is what happened to that telescope. So then we moved to Lick Observatory, and there was a big fire there that almost got to our SETI telescope right here. So then we moved to Arecibo, which was until recently the world's largest radio telescope. And this is what happened to the Arecibo telescope. You might ask, why is all this stuff happening to Dan? Why are all these telescopes collapsing? And the answer, according to the World Weekly News, is that these telescopes have been zapped by hostile space aliens. They did not want to be discovered, and they zapped these telescopes. So a simple thing to look for in our early SETI searches was just kind of we call a narrow band signal. These are different channels, different frequencies, and we're listening to lots of different frequencies. Here's channel 2,264,191. Here's channel number 2,264,703, and here's a channel that's got some strong signal. So it's kind of like tuning your radio dial across the spectrum, looking for a strong signal. That's the kind of thing that gets our attention. We don't actually tune one channel at a time. We've got a technique where we can listen to many channels at once. That speeds up the search. Then we wanted to kind of branch out. We want to look for signals that are drifting in frequency. So here are signals that are, instead of staying at a constant frequency, like these signals are changing. Whoops, sorry. This one's going up in frequency. And these changes in frequency might happen if a transmitter is on a planet that's spinning around the way Earth is spinning around. And those accelerations introduce these Doppler shifts and change the frequency that we observe on Earth. So we want to look for these kind of signals. Pretty easy to pick out these patterns with your eye, but we have about 100 million of these things every second to look at. Computers can do this too, but it needs a lot of computing power if you want to look at 100 million of these things every second. We also want to look for pulses. This is a bip, 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 a periodic pulse. And I've circled these pulses, and that makes it easy to see there's a pattern here of repeating pulses. If I took the circles off, though, you wouldn't be able to pick this out with your eye unless you maybe studied it for hours and hours. But the computers can do this. We have 100 million of these things to look at every second. You need a lot of computing power to do that. As Tucker mentioned, one of the projects that we put together about 20 years ago was this project called SETI at Home, where we asked people around the world to help us with their computers at home. And we stored about a petabyte of data from the Arecibo telescope. We broke it up into little pieces, send it out to volunteers with their laptops and their cell phones all around the world. If you want to participate in SETI at Home, actually it's in hibernation, as Tucker said, but if you did want to do this, you download this free screensaver program. And when you go out for a cup of coffee, this program would pop up and not just put up pretty pictures on your screen, but actually go through the piece of sky that you've been assigned, go through all the different frequencies and all the different patterns, and try to identify interesting things. And your name is attached to that data. If you find ET, you might get the Nobel Prize in that parking permit that I was talking about. We had about 8 million people sign up in 226 countries, and together these volunteers formed one of the biggest supercomputers on the planet. So we were able to do the most sensitive search that's ever been done thanks to these volunteers. It would have been impossible to afford a full-time supercomputer for 20 years. Well, we haven't found ET. I'm a little uncomfortable arguing, well, just give us more money because we have these spin-offs, but I'll just mention this anyway. We developed some educational curriculum. Kids really excited about this question, are we alone? It's got good hooks into how does life get started, biology and chemistry, and you can learn astronomy and evolution and physics. There's a lot of subjects that are touched on by addressing this question, are we alone? We developed this open source system where you can use your home computer, not just to participate in SETI, but there are now 100 different projects that you can use. There's climate change projects. This is working on gravitational wave detection, searching for planets, protein folding. You can work on COVID drugs. You can work on HIV drugs. You can work on malaria drugs. We also worked on these citizen science projects where volunteers can use their brains and their eyes to do work. Our first project was called Stardust at Home, where we brought back dust from a comet, from the tail of a comet. And in this aerogel that was out there scooping up the dust, there are little microscopic particles. And we've made millions of pictures in this microscope, and the volunteers would go through them and see if they could find the particle. That helps us figure out what the comet is made of. We also went out and scooped up some of the dust that was around when the planets formed, and that helps us figure out how the planets formed. So now there are a lot of these citizen science projects where you can, so instead of just using your computer or your cell phone to do computing, you can also use your eyes and brains to help these different science projects. It turned out that the instruments that we developed for SETI were these very powerful signal processing instruments that could do very high speed real-time computing. And they ended up getting used for all kinds of astronomy discoveries. You probably know about these black holes. The very first images of the black holes were made with these SETI instruments. Fast radio bursts were discovered with using SETI-based instrumentation. Most pulsars were discovered using SETI-based instrumentation. A planet made out of solid diamond was found with SETI-based instrumentation. So the instruments that we developed originally for SETI were adopted by our colleagues, and we helped them. It's used outside of radio astronomy in medical research. We're trying to get data out of a brain where you implant electrodes. We used radio links to get data out of a brain. The eventual goal was to control a prosthetic arm by thinking about where you want your prosthetic arm to go. Our big spin-off is we've had a couple hundred students that have gone through our group. Some of the highlights are Pierre, who started one of the early self-driving companies. He put together these LiDARs, these bubbles on the roofs of self-driving cars, sold his company to Google, and they developed turned into the Waymo. Pierre retired very young. Shelley Wright worked with us on SETI. She's still doing SETI. She's a professor at UC San Diego, and we're still working together on a project called PanoSETI. I'll tell you about like that. Aaron Parsons worked with us on SETI and now is using the skills he learned in SETI. He's a professor at Berkeley to look at how the very first stars and galaxies developed. He's building a big telescope in South Africa to learn how the first stars and galaxies formed. Let me tell you a little bit about future SETI experiments, and then we'll talk about, well, I think we'll have time for questions, I hope. A new telescope we're working on is even bigger than Arecibo in China. Is the FAST telescope. This is 500 meters across, holds about 20 billion bowls of cornflakes. And we're doing a big sky survey at this telescope. And we're doing it together. There are people looking for pulsars. There are people mapping the hydrogen in the galaxy. There are people looking for fast radio bursts. And then our group is going along for a ride while all these other groups are working, doing their sky surveys, and we're looking for ET. The next big project of Breakthrough Listen is on a prototype of this telescope called Meerkat. This thing doesn't exist yet. This is an artist's conception called the Square Kilometer Array, made out of thousands of radio telescopes. Right now, there's a prototype in South Africa called Meerkat with 64 of these dishes. And if you have a big array of dishes like that, you can look at a lot of stars at once, and that'll speed up the search enormously. A project I mentioned that I'm excited about that I've been spending a lot of time on is this thing called PanoSETI. And it's work being done at UC San Diego and Berkeley and Harvard and Caltech. And the idea is to cover a large part of the sky all at once. We call it all sky all the time, looking for flashes, optical and infrared flashes in the sky. We call them transients. The problem is we don't know where the transients might go off. So your telescope is pointed over there, but you miss it because the flash is going off over there. But if we build a thing that can look kind of everywhere at once, each one of these telescopes covers 100 square degrees. We hope to have about 100 of these things. Right now, we only have a couple. We started with this thing at Lick Observatory that could look at kind of one star at a time. And then we could point it to one star, then the next star, then the next star. I don't know if you can see this animation, but this is kind of the way it worked. You could look at one place on the sky at a time. What we very recently, these detectors that used to cost tens of thousands of dollars, that's why we could only look at one place in the sky. Now they're $5 each, so we can tile the whole sky with these detectors that are used in medical imaging, positron emission tomography. And that's what made it cheap. And we can use these things combined with these big plastic lenses called Fresnel lenses, so we can build a cheap big telescope. And right now we just have actually 3 telescopes. This one just shows 2 on the mountain at Lick Observatory, which is up, it's about a 2-hour drive from here. I recommend, it's near San Jose up in the mountains. They give tours and you can walk around. It's a beautiful place to visit. And they have nights where you can look through some of the telescopes. The thing that I'm excited about at Panel SETI is it explores a kind of search space that nobody's looked at before. We're looking for short pulses like flashes from nanosecond, billionth of a second, microsecond, a millionth of a second, a millisecond pulses. Nobody's really looked at that before. And it turns out in astronomy, if you look at something that nobody's looked at before, a new time scale in this case, or a new wavelength or frequency scale, or a new size scale, or you can look for much weaker objects. Whenever you do that in astronomy, you find some new phenomena. So if you want to make a discovery in astronomy, just look at something, look where no one has looked before. That's not a physical law. We don't understand why it works, but it turns out the universe is kind of populates at phenomena at all different size scales and wavelengths. We don't know why that's true. I'm optimistic in the long run because radio telescopes are getting better. This is an exponential growth. The computing power is getting better, as you know, with exponential growth. We used to listen to 100 channels when I was a grad student. Now we listen to 100 billion channels. If you kind of look at the growth of SETI, here's a kind of one channel, 65,000 channels. Now we're at 34 billion channels. This is, I won't get into this because we got to go. Eventually, Earthlings might be able to use the sun as a gravitational lens. The sun bends light, and you could put a camera at the focus. Unfortunately, you got to get out way beyond Pluto. We don't know how to do that. Put the camera there. But if you could do that, you got a big telescope the size of the sun. You could have 10-meter resolution. You could see buildings on an extrasolar planet. A couple of my favorite quotes. Phil Morrison said that SETI is the archaeology of the future. It's going to be hard to find these primitive civilizations like us, but we might find a more advanced civilization first, maybe a billion years ahead of us, and we could learn what's in our future. How did they get through their bottlenecks? We could learn all the poetry and music and medicine, and maybe they'll tell us how to get on the galactic internet, and they'll tell us about all the other civilizations that they've been talking to. Carl Sagan said that SETI's profound either way. We find ET that could have be interesting to know that we're not alone. And if we do a thorough search, which we can't do now, but eventually if we could do a very thorough search and say, hey, there are no evidence of technology out there, that might indicate that we really are alone as an intelligent technological civilization. And that's very profound. That means we got to take incredibly good care of the very precious and rare life on Earth. Summary and conclusion, no ET so far. We're still working on it. I do have a couple more slides. The SETI Home volunteers have sent out haikus. They send money to keep the students going. They help us write the code. They find bugs, they speed it up. They do a lot of great things, but they've also sent us haikus. They've sent us thousands of haikus, which you can read on the website. But I just read you a couple of them. Paula Cook, searching for life, answers are revealed about ourselves. And Dan Seidner, 1 million Earthlings, bounded by optimism, leave their PCs on. Well, thank you very much. And Tucker, I think we have time for questions and comments.
I think we do. Dan, that's great. I see one question, and I'm going to pepper the assembly of questions with my own soon. Stuart, a wondernaut of some fame at these Zoom events, asks, do we have a playbook ready to go for when that first contact day comes? Who wrote the playbook? Where can we find it to read it? Does it cover a wide variety of scenarios for such communications or visits?
Yeah, Stuart, there is a protocol. It was developed by an international organization called IAA, the SETI Permanent Committee, and it's been kicked around now for about 30 years. And you can read about it if you just I think if you Google something like SETI protocol, you'll find this. And the protocol calls for, before you make a big announcement, you ought to make sure that it's something interesting and it's not a graduate student playing a prank on you or a bug in your software or a satellite going over. There's a big problem in SETI that you think you found a radio signal from ET, but it's really from T. It's caused by radio interference, radio pollution from terrestrials, television, satellites, cell phones near the observatory can kind of trick you. So the protocol says, well, get an independent group with different telescope, different people, different software, different instrumentation, and get them to see if they can confirm the signal. And if you both look at it, you can kind of triangulate on the object and measure its distance and make sure it's not some nearby thing like a satellite that was made by Earthlings, and you can make sure that it's far away. And even at that point, you probably would say, we found something really interesting and these are the coordinates. Oh, the other part of the protocol is once you make this announcement, once you've had independent verification, you make the announcement public and you share all the information. So the announcement might say, there's some really interesting signal. These are the coordinates in the sky. These are the frequencies. This is all the information we know about this signal. Because it may be some new astrophysical phenomena that's generating that. It may not be ETs. And then you would imagine a lot of people start looking at it from all over the world using a lot of different facilities and try to learn more about it. That's about as far as the protocol goes. And you kind of tell it addresses mostly the kind of radio or maybe optical infrared detection of a technosignature. So I think we need a lot more work, and it'd be nice if we could get countries and governments to agree to this rather than just a kind of small group of astronomers that do this kind of research.
Yeah, Stuart, I'm sorry I didn't let you speak your own question. If anyone would like to ask their own question, please raise your hand first, and then we'll acknowledge you and you can unmute yourself and turn on your webcam. I understand there's a second part to Stuart's question. I just want to give you a chance, Stuart, to ask it yourself if you'd like. I know in the past you've been willing to do that. Would you like to, Stuart?
Yes, Tucker, thank you very much for bringing Dan to us tonight. And I guess historically speaking, Dan, thank you for bringing Tucker to us too. So yeah, my second question would be, again, I've heard through media that Stephen Hawking felt that maybe we should keep a low profile because the aliens that we might be reaching out to might not have good intentions. What do you think of that?
Yeah, I actually agree with Stephen Hawking. So what Hawking was talking about there is something called METI, Messages to Extraterrestrial Intelligence. There's a small group of people, the majority of scientists and astronomers do not think this is a good idea, but about 1% of the astronomers think that it's a good idea to deliberately transmit messages out to other civilizations. And they're saying, well, yeah, what if everybody's listening the way we are? We're doing what's called a passive search. The standard SETI search is just listen and see if we are alone, see if there's anything out there that's interesting. But active searching, or METI, would be to broadcast signals out to ET, intentional signals. And their argument is, well, Earthlings are already doing that. We're sending out television and radar. But the counter argument, well, these are beam signals that are sent anti-cryptographic, that contain a lot of information. They're sent to nearby stars. They're very powerful signals. They are different from the current footprint of Earth. And what some people think, including myself, is that this thing maybe has low risk, but it's very hard to assess the risk. But but sort of giving off the presence of Earth and our technology, the ET might not be might come and eat us or grind up our planet and get all the palladium out of the earth or something like that. So I don't know what the risks are. Maybe they're all really nice and they want to help us out, but maybe not. But I think even if the risks are small, this kind of activity is putting 7 billion people on the planet at risk. So, you know, even if the risks are 1 in a million, every time you do it, you're on average killing 7,000 people. You know, if the risks are 1 in 1,000, you're killing 7 million people every time you transmit. So the risks are small, but there's a lot of people you're putting at risk. And so I think if you want to do something like that, it shouldn't be just a small number of scientists that get together. Oh, let's transmit. It should be a decision for all humanity. People in different countries should get together and discuss all the risks and the potential benefits. And there should try to be a kind of consensus about this. There's a kind of similar thing if you want to do research in maybe if you want to do research in some dangerous bacteria like smallpox virus or something like that. There are risks involved. You might learn about smallpox and prevent other diseases, but you might let it out accidentally out of your lab. Most people are no longer vaccinated against smallpox. You could kill a lot of people.
Stuart, thanks for your questions.
Thank you. Thank you.
All right, Dan, I'm going to let you have one. Do you have any strong opinions or insights regarding the search for unidentified flying objects? I guess they're called UAPs now, but is there indeed a government effort to look for unidentified objects in the sky that might be of alien origin?
Yeah, I think there's recent effort by some government organizations to try to figure out what is causing these things. A lot of people think that UFOs are caused by other civilizations visiting us. To me, that is extremely unlikely. There's no evidence for any of that. Some of this is, there are different explanations for these unidentified flying objects, or UAPs they're called now. So a lot of them are real. And we know they're real because people call us and say, hey, I see this UFO in the sky. And what they're looking at is the space station going across the sky. They don't know what it is, but they see this very bright thing. It's moving across the sky very fast. Sometimes they embellish it. Instead of just saying it's, you know, a bright thing moving across the sky in a few minutes, they will say it's got windows or something like that. But a lot of it's real. They see aurora or they see a rocket launch. They know what it is. When the rocket flies by from Vandenberg, you don't know it was launched from Vandenberg, but you see these brilliant lights moving across the sky. It's quite beautiful and quite unusual. We get a lot of calls, you know, UFO, and it is, they're unidentified. So some of it's real, some of it's imagined, and we know that because it correlates very well with what movie came out. Nobody saw a flying saucer until Jules Verne wrote about flying saucers. Before that, people saw angels. After Jules Verne, they saw flying saucers because he wrote about them. And a lot of the descriptions correlate with kind of what's in the popular literature or more recently in movies. Not that people are lying about it, they're just kind of confused. They've seen a movie, they dream about it or something. And it's hard to know what was in a dream or what you saw. So some of it's real, some of it's kind of imagined, suggested by the current culture. Some of it is deliberate hoaxes. Von Däniken, you know, wrote Chariots of the Gods about all these different things. These crop circles, these are made by kids, you know, they have competitions. They're not made by ET. The Nazca Indians made these beautiful, huge objects in the plains that are, I think, maybe 1,000 kilometers across. Beautiful things that people said, oh, they could only be made by ET. Some people say the pyramids could only be made by ET, but we understand who made them and what the cultural drivers were for those kind of things. There's no evidence that any of this stuff has anything to do with ET, but I think it's still worth studying it. It could be something that kind of mundane, camera optics, digital signal processing, image artifacts, but it could be something new, interesting, new atmospheric phenomena or something.
All right, thanks, Dan. Early in your talk, you told us about the best scientific estimates of the number of planets in the Milky Way. Given that we know the number of stars and we now know that the average star has about 5 planets, you came to the number 1 trillion planets in the Milky Way. And then we have reason to believe that about, I think you said 5% of those are in the habitable zone, where liquid water could last on a planet long enough for some interesting chemistry, perhaps, to take place. 5% of a trillion is 50 billion habitable planets in the Milky Way. I mean, that just sounds remarkably hopeful that it just seems hard to believe that we don't have some kind of cosmic company, even if it's just slime somewhere out there in the Milky Way.
Yeah.
Are you at all surprised that some of those slime worlds have progressed in the manner you described, where they're now intelligent and technological enough to travel the distances between the stars? And this raises the Fermi paradox, Fermi question, let's call it that. If life, even intelligent life, is as common as we hope it is, where is everybody? If I haven't characterized Fermi's question properly, please enlighten me, and please give us your best answer to the Fermi question.
Yeah. Oh, by the way, I was just talking about the number of planets in our own galaxy, the Milky Way. I forgot that there's 1 trillion galaxies as well. So you got to multiply all the numbers you were just mentioning by another trillion. So yeah, a lot of places for life. It would be bizarre for alone. And that's what Fermi was talking about. It said, this was in 1950, he was having lunch and he said, where is everybody? And I think everybody at the table, which are listed there, immediately knew what he meant. And what he meant was, if there are all these civilizations out there, some of them are 1 billion years ahead of us. Surely they know a lot more about flying around than we do, and they could build self-replicating spacecraft, and pretty soon they could be all around the galaxy. And why aren't they, landing at the UN Plaza? And so the idea is that if you don't see them landing at the UN Plaza and flying all around, conquering the galaxy, does that mean that there's no intelligent life out there? I think that's what he meant by the Fermi paradox. And so this is kind of a restatement of the argument. Some stars are 10 billion years old. So some civilizations are, billions of years ahead of us, zooming around the galaxy. We should have seen them. And therefore we haven't seen them, so we are alone. That's the syllogism. So there's some good books about that. And I like this book on this that listed second. If the universe is teeming with aliens, where is everybody? It originally, first version, called 50 Solutions to the Fermi Paradox. Now it's up to 75 in the second edition. It's a fun book. And I'm not going to tell you all 75 solutions, but I'll just mention them. But one possibility is space travel is hard, takes a lot of energy, stars are far away. I actually don't think that's the reason. I mean, they could just go slowly. That doesn't need much energy. They could scoop up fuel on the way. They can sail with lasers. I think, it's hard for us, but any civilization worth its salt is going to know how to do this. Another possibility is right now we're in kind of a exponential growth phase. We like, more money, more stuff, fast cars, but maybe when we get a little more sophisticated, we are not going to be in this exponential growth, and we're going to be more interested in poetry and music. And they're not in this exponential growth phase anymore, which is unsustainable. They've stopped exploring. They're learning about the galaxy. They're studying it, and they stay at home. Another possibility is they destroy themselves. As soon as they get this technology, they wipe themselves out. So another possibility is the prime directive. If you watch Star Trek, you know that if you're in Starfleet, you're not allowed to go messing around with primitive civilizations that are just emerging like ours. And because that would be interfering with their evolution and their culture. And maybe they're interstellar police in case some rogue civilization wants to interfere with primitive stuff, civilizations like ours. Another hypothesis that I didn't mention is that the zoo hypothesis is that maybe they do know about us and they're kind of watching us the way that we watch things in the zoo. You know, they're keeping an eye on us, and maybe if we get a little smarter and stop killing each other, they'll get in touch. Anyway, there are lots of ways to get out of the Fermi paradox.
Great. Dan, thank you. Your timing is remarkable. I'm wondering if the Wondernauts have any more questions for you, because if they don't, we've got to draw this evening to a close. Boy, Dan, thank you. Thank you to everybody. So I do thank you, Wondernauts, for being here tonight, especially those of you who are donors to Wonderfest, patrons even on giving regularly. Thank you for helping to keep Wonderfest alive. I also, of course, want you to join me in giving at least an American Sign Language silent applause, or perhaps turn your mics on and give them a loud vocal applause. Dan Wertheimer, thank you very much for tonight.
Thank you, Wondernauts. It's been great talking with you.
All righty.